Hello and welcome. If you've ever worked with sequences, signals, or really any kind of discrete system, you know it's absolutely crucial to understand the relationships between your solutions. Well, today, we're going to demystify a really powerful tool designed for exactly that, the Casorati Matrix. Okay, let's get right into it.
So here's our game plan for today. We're going to start with the basics, what even is this thing? Then we'll get our hands dirty and see how to actually build it and find its determinant. After that, we'll get to the main event, its most important job, the test for linear independence. And we'll walk through a real example. And finally, we'll connect it all back to the real world and see where this tool really makes an impact. It's a clear path from theory straight into practice.
All right, first things first. Let's peel back the layers and ask the big question. What exactly is this Casorati matrix? Let's lock in a clear definition. At its heart, the Casorati matrix is just a special type of square matrix that you build from a set of sequences. Its whole reason for being is to help us analyze these sequences, especially when we're talking about linear difference equations, which, let's be honest, are the foundation for so many discrete systems out there. Now, probably the best way to wrap your head around this is with an analogy. If you've ever studied differential equations, you've almost certainly run into its cousin, the Wronskian matrix. The Wronskian does this kind of work for continuous systems, smooth functions and their derivatives. Well, the Casorati matrix does the exact same job, but for the discrete world of sequences and time series data. It's the perfect counterpart. All right, so we know what it is. Now let's get into the how. And the great news here is that building one of these is actually a surprisingly straightforward step-by-step process. No magic involved. Think of it like a simple recipe. First, you just gather up all the sequences you want to test. Second, you line them up, and that becomes the very first row of your matrix. Easy enough, right? Third, and this is the key move, you create the next row by calculating the forward difference for each sequence. That's just a fancy way of saying the next term minus the current term. You just repeat that process for each new row. And finally, that number you get when you calculate the determinant, it's so important it gets its own special name, the Kazoratian. And here's what that structure looks like in practice. Let's say you have 3 sequences. You end up with a 3x3 matrix. You can see it right here. That top row is just our original sequences. The second row, with the delta symbol, is that first difference we talked about. And the third row? Well, that's just the difference of the differences. You see how it just builds on itself? It's a really clean and elegant structure. So, we've built our matrix, we've calculated its determinant, the Casoratian, but so what? What does that number actually tell us? Well, this brings us to its most powerful, most common application, the test for linear independence. And honestly, it all boils down to one simple golden rule. If the Kazoratian is anything other than 0, bam, your sequences are linearly independent. It's that simple. A non-zero result is the definitive proof you need that no single sequence in your set can be created by just combining the others. But check this out. It gets even deeper. When all your sequences happen to be solutions to the same linear difference equation, this test gets supercharged. The result isn't just a snapshot. The Kazoratian is either non-zero for every single value of k, or it's 0 for every single value of k. It's all or nothing. This tells you that linear independence isn't just some fluke. It's a fundamental, unchanging property of that entire system of solutions. Okay, enough theory. The best way to really get this is to just see it in action. So let's roll up our sleeves and walk through a concrete example. We're going to take 3 simple sequences and put them to the test. So here are our test subjects. First, we've got a super simple one, just the constant 1. The second is an alternating exponential, -2 to the power of k. And the third is a classic growing exponential, 3 to the power of k. The big question is, are these 3 truly independent of each other? Let's build the matrix and find out. Now, to make life easy, let's just evaluate this at k equals 0. The first row is a piece of cake. Anything to the power of 0 is 1, so we get 1, 1, and 1. For the second row, we calculate those forward differences. The difference for a constant sequence is, of course, 0. For the other two, a little bit of math gets us -3 and 2. And for that final row, we take the difference of those differences, which leaves us with 0, 9, and 4. And there it is, our matrix. All right, moment of truth, let's calculate the determinant. So we've got 1 times -3 times 4 minus 2 times 9. That's -12 minus 18, which gives us -30. And the big question is -30 0? Nope. And because it's not 0, our golden rule tells us with absolute certainty, yes, these 3 sequences are linearly independent.
Okay, so that's a neat math trick, but you might be wondering, where does this actually matter outside of a textbook problem? That's a great question. Let's talk about the key areas where this test isn't just useful, it's absolutely essential.
This is why this should matter to any researcher or engineer. When you're solving a difference equation, you have to verify that your solutions form a fundamental set, basically a complete toolkit for all possible solutions. The Casorati Matrix is the tool you use for that. It's crucial in signal processing for things like analyzing digital filters, it's essential in numerical analysis for understanding error, and it's used all the time in discrete dynamical systems. It's a foundational check for anyone building models of the discrete world.
So as we wrap this up, I want to leave you with a question to think about. Whether you're working with population models, financial data, or digital signals, where in your own research could this definitive test for independence bring more clarity and more rigor? It's an incredibly powerful tool to have in your analytical toolkit. Thanks so much for joining this explainer.